This next problem is about Kirchhoff's rules, and it says determine the voltage across the 5.0 ohm resistor in the drawing. Which end of the resistor is at the higher potential? As you can see, well, there is a current flowing through the 5 ohm and then it splits up here and it goes in there, but notice there's a positive potential here, and then there's a positive potential kind of opposing them from the other side. So in which direction is the current actually flowing? For complicated circuits like these, Kirchhoff's rules, the junction rule and the loop rule, come in very handy, because here it's virtually impossible to determine what is parallel, what is series. If these two batteries weren't here, then we could actually do the problem, but they were there. So, I mean, we could do the problem with series and parallel circuits, but these two batteries are there, so we have to deal with them in a different way. I figured I'm going to start this problem out with actually doing the circuit on the FET circuit construction kit. And so I'm going to put a resistor here and there and there, and then I put a battery and another one and another one, and let's see, they're all turning up like this, like that, and like that. There we go. And yeah, I could connect those two here, and then I can connect here and I can connect here. You can see that from the drawing, that's exactly the same if I put the junction here or if I slide it over there. It's just a piece of wire in between, so that's exactly the same. And then over here I put a little wire there and a little wire here, and then I connect over here and over there, and there is my circuit. And interestingly enough, nothing happens on FET. Oh, maybe I should adjust certain things, such as the resistors. 5 ohms. And actually, I think I'm going to do the voltages first. It says 10 volts on this one. And, oh, there, something happens now. All right. And 2, and the other one was 15. There we go. And this one here is 10. And this one here is 10 as well. Oh, there it is, 10 as well. Okay. Well, that pretty much answers one already. That is, the current flows from here, from the positive to over here, the negative. Despite of that, this one is a positive terminal, but notice that battery is kind of opposing what, especially this battery here, which says what this battery produces. Interesting enough, this is the highest voltage here. Oh, you know what? I have to think of something here. One moment. I have to look at FET, which way they actually put the current. If they put the current from the positive to negative, or if they show the electrons flowing. Oh, they show the electrons flowing. Okay, so the electrons are, of course, flowing from negative to positive, which means the positive end is over here and the negative end is over here. Again, as you learned in the book, that the electrons are flowing in one direction, but the electric current is defined as the opposite direction. So positive is here, negative is there. Respectively, this is at the higher potential than this one. Okay, overall they also want to figure out which end is a higher potential and terminal voltage across the 5 ohm resistor. So what I'm going to do is I'm going to grab myself a voltmeter. Oh, there it is, I guess. Put it there, and I put this one there, and I put that one there, and it reads 0.75 volts, and I'm done. That was actually relatively quickly to do, except that the proper way. I still have to do the proper way, and that's going to take a while because Kirchhoff's rules involve systems of equations. In this case, I will just use the systems of equations with substitution and elimination methods, or otherwise, if it becomes more complicated, one could use also matrices instead of systems of equations. But in any case, let's do it on paper. So the analysis, the proper analysis. There are 3 loops here and 2 junctions. The junctions are easy to see, 1 and 2. And the loops are, of course, the entire thing is 1 loop. And here on the left is 1, and on the right is 1. So 3 loops, 2 junctions. Setting up the equations for those currents and the voltages would produce 5 equations. Well, we would have to look at how many variables do we have, and therefore how many equations do we need. Well, they want us to figure out what the voltage is on this one. So that would be a variable, an unknown. Notice that we don't know what the voltage is on this one. We don't know what the voltage is on this one is. We don't have to figure them out. However, these are unknowns as well. So 1, 2, 3. We have 3 unknowns. We have 5 equations, which means actually we kind of have an overkill if we write them all down. Therefore, among those 5, we choose 3 to match the number of variables we got, and those are the ones that we write down. Among the 3 loops, it makes sense only to write 2 down. For example, we write the one here on the left down, and we write the one on the right down. If we also took the entire loop, well, you can see if you put the right loop and left loop together, you come up with the entire loop. So what that would mean is that the entire loop as an equation becomes redundant. You can just take the equation on the left and the equation on the right, put it together, you come up with the entire loop, so you haven't gained anything. So therefore, we're only going to write down the loop on the left, the loop on the right, and then one of the 2 junctions. And as far as one of the 2 junctions here, this one is a whole lot more comfortable to write down. The current going through this one here splitting up into these 2 components, or current going through this one here and splitting up to these 2 components. Okay, let's write them down. The loop rule on the left. The 10 volts over here. So loop on the left. Okay, I didn't mean to write that in blue and red. I'm going to use black. So the loop rule, the loop on the left. We have 10 volts, so 10.0 volts. And that means everything else here, here, here also has to add up to 10 volts respectively. If I go 10 ohms here, then I would have to step down, step down, step down, step down until I come to the other side, 0, and I'm back to 10 when I go through the battery itself. That's just another way of expressing it. Respectively, 10 volts equals 2 plus this plus this. So I'm going to write that down. 10 volts equals 2.0 volts plus the voltage in the resistor in the middle plus the voltage in the resistor on the upper left. Here I can already write a little bit down. I think I'm going to change color. So to abbreviate a little bit, I leave out the 0.0 there, but we keep in mind those are 2 significant figures because of the 2.0 here and the 5.0 there. Plus, and now what I'm going to do is for the voltage in the middle, I'm going to say I got the current for the resistor in the middle times its resistance, which is 10 ohms, plus the current for the resistor on the upper left times its resistance, which is 5 ohms. And at that point, I may want to define of what I'm saying here is that saying that the 10 volts is applied here and the current would flow this way. not the electrons, but the electric current. The electrons, of course, flow in the other direction. So I have a plus minus here, and then it splits up into this part. So again, I have plus minus here. Whoops, plus minus. And then I have to see, well, I have to make a judgment. Oh, it looks like 15 is pretty strong here, so probably the current is going to flow through here. And I have plus here and minus, minus there. And then, as I said here on the loop on the left, this one is 10 ohms minus this one, minus this one, minus this one equals 0 coming back here. And of course, when I have minus, minus, minus right here, I put it to the other side, and of course I come up with positive numbers. So all of these three here add up to be the 10 volts. Okay, that's the loop on the left. The loop on the right would be similarly 15 volts here, minus this, minus that, equals 0 all the way back. Respectively, if I get that minus, minus, minus to the other side, I'm going to have 15 volts equals 2 plus this one, plus this one. So I'm going to have 15.0 volts equals, let's see what this one is. Oh yeah, there's the 2.0 volts plus the voltage in the middle plus, trying to make myself a plus here, there we go, the voltage in the upper right. And again, color change. So I have 15 volts equals 2 volts plus IM times 10 ohms plus I upper left times 10.0 ohms or 10 ohms. There you go. Okay, I explained that if we put these two equations here together, we'll actually come up with the entire loop, and we could write that entire loop down, but you will see that it's redundant, that putting these two equations together yields actually the third loop, the entire loop, and we wouldn't have gained anything. So we have to use one of the junctions, and again, the upper junction makes a lot more sense. Upper or top junction. So the current flows in here and it flows in here, and then it gets together and flows through here. Let's see, by the way, one thing I forgot earlier to say is that with putting these potentials here, plus, minus, plus, minus, minus, plus, I did that arbitrarily because at this point I was just guessing there's probably going to be plus, minus, and then here minus, plus because of the small battery here, but I didn't know that for sure. Actually, I could have looked at my animation earlier and cheated and have that found out that way, but I don't know it. So what would happen if this is actually incorrect here? Well, what would happen is that one of our, let's say this one here would be incorrect, that this one is actually plus and minus. What would happen then is that the current that we come up with would have a negative attached to it, and that would tell me I have to turn it around and come up with the right one. If, in this case, all our currents come out to positive numbers, then I actually have chosen all of three of them correctly, but we can see that later. Okay, anyway, on the upper junction, this one plus this one equals that one, so I upper left plus I upper right equals I middle, is what I called it. Respectively, I'm going to put that all on one side and explain in a little while why. So I put it all on one side. That means that I have 0 equals IM minus I upper left minus I upper right. I know my R looks like a V, but my tablet here is not totally adjusted to give me a nice handwriting. Okay, now I actually need more space. So gonna scroll down here a little bit, extend my page, and now I'm gonna grab the equations that I have here. Put them all there. 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 I bet that I need even more space, so there we go. Alright. Okay, and now I'm actually gonna get rid of some stuff that I don't need if I just want to look at the equation. So I'm just gonna get rid of the units here, the volts, as well as the ohms. There. But I leave my variables there. And maybe I can make my 10 look a little bit nicer again. Okay, and notice what we have now. We have a system of equations. System of equations with 3 variables or a matrix. In fact, I will write it as a matrix here. I'm gonna use yet another color. And still some more space. I'm gonna start with the last one first because it looks a little bit nicer to me. Here I'm gonna write down, let's see, my matrix. I am on this is going to be the first entry, so it's going to be a 1, I upper L, negative 1, I upper R, negative 1. So what I have here is, here's my variable IM, here's my variable IUL, and here's my variable IUR. So 1, negative 1, negative 1, as we can see here, 1, negative 1, negative 1, and that equals 0. My second equation, well, there's my IM, and there's a 10. There it is. There's my IUL, and there's a 10. There it is. There's no IUR, which means it has to have a 0. And on the other side, we'll subtract the 2 from the 15, which I believe is slightly out of the screen. So subtract the 2 from the 15, I come out with 13. For the first one, IM carries a 10. IUL carries a 5. And I just noticed I must have made a mistake. I'll fix that in a moment. IUR, there is no IUR, therefore it's 0. And then I have 10 minus 2 is 8. Okay, I need to fix my mistake because my middle loop here has to involve IUR, so let me check that. I think that was just a typo. You might have caught that earlier. Yeah, right there. There it is. VUR, and then inexplicitly I wrote IUL. I don't want to record the whole thing over again. If I was in the classroom, I would ask people, as soon as you see me make a mistake, mention it. Of course, there was nobody here who could have noticed that. You may have noticed it on your own earlier, but you weren't able to tell me, of course. And as you may recall from algebra, that's actually what happens occasionally with those systems of equations and matrices, that there's so much stuff involved, so many numbers, so many equations, that it's easy to make a simple typo mistake. And yeah, it's kind of, in this case, it's really convenient to just go back and fix it, because all I need to do is take the IUL off here and write IUR. There it is. In fact, I think I'll write it in green so it kind of stands out that I had fixed it. And that also means that this one here is an IUR. There it is. And that means that down here, these two entries have to be swapped. So there's a 0 and there's a 10. And there's a matrix. Whoops. My line came out really strange. So here's my matrix, which I try to solve on the graphing calculator in a moment, which then the way I'm going to solve it is that I get entries here of 1, 1, 1, which are the three variables, and then I'm going to get some entries over here, which of course is going to tell me what those numbers are, each one of them in amps. I actually just noticed that I was supposed to get voltages, but that's alright. I'll just fix that later. And actually it's going to be way more convenient to just determine the electric current and multiply then when I have it here later on with the 5 ohms. But let me grab the graphing calculator. Okay. Let's see, don't need this. Alright. Here we go. Matrix. Edit. Guess doesn't matter which one I use. Okay, it's going to be a, let's see, 3 by 4. Yeah, 3 by 4. And here are my entries. 10, 5. I said earlier I do systems of equations, but then I noticed I actually have 3 equations in 3 variables, and the matrix is going to be easier. There we go. And what was it again? There's 1, negative 1, negative 1, and 0. Okay, done. I get out of this. I look at that matrix on the home screen, and 10, 5, 0, 8, 10, 0, 0, 10, 0, 10, 13, 1, negative, and negative 1, 0. Okay, then I'm going to go to the matrix, math, and here is what solves the matrix right away, the double REF. And I tell it matrix A, and I'm going to hit the enter button, and I really cross my fingers that I come up with the right result, because if I don't, I must have made a mistake somewhere, and because it's matrix, it's systems of equations, it's going to be tough to find that mistake. So I cross my fingers that I did everything correctly. Here we go. And I'm supposed to, oh no, these are the currents. These are currents. So in the middle current here it says 0.725 amps. The upper left it says 0.15 amps. In fact, I can already see that because I know it has a 5 ohm resistor that I multiply the two, I come up with 0.75 volts. And here it's 0.75 times, yeah, 575 amps. Okay, so that's what I'm going to write down. Those are the amps, the currents. So let's see, 0.725 amps. That's the upper middle one. And then, no, not upper, just middle one. It's a long problem. You know, you can say something that's just slightly off, and it does matter. So 0.15 amp, that's the upper middle, the upper left. My goodness. And then this one here is the 0.7. Boy, oh boy. 0.575. I did it correctly, and I want to write it down correctly. So that one is the current on the upper right. And the one that we really need is this one here, which of course is this one here. And And what we have to do for that, I think I'm running out of colors, so I go back to black, is that the voltage in the upper left equals the current that I just calculated, I on the upper left, times the 5.0 ohms that was given in the problem, and that equals, well, 0.75 volts, just like we saw earlier in the circuit simulator.